We love trying to fit our world into neat, predictable patterns, but what happens when reality just doesn't play along? What happens when we get hit with a massive, unpredictable event that completely shatters all the averages? Well, today we're going to dive into a new approach that aims to do just that, to tame that very unpredictability. Okay, so we've all seen this shape before, right? The bell curve. Officially, it's called the normal distribution, and it really represents this tidy, almost comforting, predictable world where most things, like, say, the height of everyone in a room, cluster right around the average. They're in the middle. And this really shows you just how orderly a bell-curved world is supposed to be. Everything's perfectly symmetric. About two-thirds of everything that happens is just, well, average. And getting a truly extreme result, something way, way out in those skinny tails of the curve, it's practically impossible. It's a very reassuring, very stable model of reality. So that brings us to our first big idea, the predictable bell curve. This is the world where, for all intents and purposes, everything is average. Right, but here's the huge question, the one that keeps risk managers and data scientists and engineers up at night. What if the real world isn't so tidy after all? And that question throws us into a totally different world, a world where extremes are, in a strange way, normal. It's time to introduce something called heavy-tailed distributions. So what on earth are they? Well, a heavy-tailed distribution is one where the tail, that's the part of the graph that represents the extreme, rare events, it just decays much, much more slowly than a bell curve. And what that means is that very large, very wild events can happen with a probability that is, well, not negligible at all. They're actually significant. And believe it or not, we run into these wild distributions all over the place. In finance, for sure, where massive market crashes happen way more often than a neat bell curve would ever suggest. In telecommunications, where a single huge download can suddenly bring a whole system to its knees. And even in the words I'm using right now, word frequencies follow a classic heavy-tailed pattern, which is absolutely critical for how today's large language models are trained. So let's put them side by side. It really makes the difference pop. In the tidy bell curve world, extremes are super rare, and the average is king. But in the wild, heavy-tailed world, extremes are surprisingly common, and they can have a huge impact. One is predictable, the other is anything but. Okay, so this creates a huge problem for the scientists and engineers trying to model these systems. They basically have two different models they've been trying to use, but they both share one massive problem. They both struggle to actually capture this wild reality. And don't just take my word for it. The researchers behind this work, Ziani, Horvath, and Ballerini, they put it perfectly. They said classical parameter estimation techniques typically fail to approximate heavy-tailed distributions accurately. In other words, our old tools just aren't cutting it. They're not up to the job. All right, let's dig into why this is so hard. Here's the first attempt, a model called BPH. See, if you look at the orange line, that's the model. It matches the blue line, the real data, almost perfectly in the main body of the graph. But now look over to the tail on the right. The model just completely falls off a cliff. It totally misses those extreme events. So it's great on the body, but it completely fails on the tail. Okay, so what about the other model, the HE model? Well, it's the exact same problem, just flipped. On the right, out in the tail, it actually does a pretty decent job of tracking the real data. But look at the body. The model's orange line is way, way off. So this one captures the tail, but it fails miserably on the body. So there it is. That's the core challenge, laid out plain and simple. We need a single model that can accurately capture both the everyday, average events in the body and those rare, high-impact events that are living out there in the tail. And this is where things get really cool. This brings us to the elegant solution proposed in this research, a true best-of-both-worlds fix. Meet the new BPHSE hybrid model. The logic behind this is actually really elegant and simple. First, you take the HE model. That's the one that's good at tails. And you use it to approximate just the tail. Then, you literally subtract that tail from the original data, so it's left just the body. Then you use the BPH model, which we know is great at bodies, to map that remainder. And finally, you stitch the two models together into one single, super accurate distribution. But wait, there's more. The researchers added a kind of secret sauce to this mix. See, a big weakness of that old HE model was that it was really sensitive to its starting settings. So they added an optimizer that automatically finds the perfect starting point, which makes the whole hybrid model way more robust and reliable from the get-go. All right, so the theory sounds great, right?
It's clever. But the real question is, does it actually work in practice? Let's get to it and see if this hybrid solution really does succeed.
And boom, here it is. This is that aha moment. The solid blue line is the real-world data, and that dashed orange line is the new hybrid model. Look at that. It is a near-perfect fit. On the left, it nails the body, and on the right, you can see on that log scale, it tracks that long, heavy tail almost perfectly. It actually works.
And it's not just a pretty picture. The numbers absolutely back it up. I mean, look at the precision here. The real values are there in bold. The old BPH and HE models on their own, they're kind of close, but they're definitely off. But the BPH-HE hybrid model, it is virtually identical to the real thing. I mean, that is a massive leap forward in accuracy. Okay, so this is all fascinating for statisticians, but why should we care? Why does a better model like this actually matter in the real world? Let's connect this theory to its real-world impact.
This is a perfect example. What you're seeing is a simulation of network traffic, a classic queuing problem. The dark blue is what's really happening in the system, and the light blue, that's what the new model predicts will happen. They are almost indistinguishable. This means we can now accurately predict things like wait times and system loads, helping us prevent those frustrating bottlenecks in everything from huge data centers to our 5G networks. So, when you pull it all together, what does this mean for the future? Well, this new tool could be a game changer. It could lead to financial models that don't just ignore the real risk of market crashes. It could mean better performance in AI that has to understand rare words and concepts. And it means a smarter design for our entire cloud computing infrastructure. It's a brand new tool to understand any system that's driven by those rare, wild, extreme events. And that really leaves us with one big final thought. Now that we finally have a tool that can model these extreme, seemingly impossible events with incredible accuracy, what's the next impossible event we should be preparing for?